Next point is to start having an overview of what the course is about. So this first class today, we will see all the topics that we will see along the course. And so these are the lectures, and actually, I didn't tell you, the intermediate exam is down to lecture 10, and then the final exam is from 1 to the end, from 1 to 20. Okay, so this is an idea that probably it will appear. You have two courses at the same time that are mine and the one of I don't know, imaging techniques or something like that. And that you will have it tomorrow. I think it is on Thursdays or Thursdays and Fridays. And it is taught by a colleague there at CC, José Luis Vilas. He's a very good guy too. And this idea will also appear with him. So we share a lot of common ideas. So the thing is that you have an object in the real world, and then you use some imaging device like a lens, and then this lens projects an idea, an image of this 3D object onto an image plane. This is a very generic model for almost all imaging tools. And then you need an energy source. That the energy source here would be light that is coming from the sun, for instance. And then the device exerts some action on the image. So it is not just an ideal image, what you get, but it is somehow processed by the device. And a very typical processing is this image inversion, for instance, that the lens is doing. But there are many more, like for instance, the lens can blur the input image. So what you get in the image plane is a blurred version of the ideal world or the real world object. And also, if you work with a digital computer or digital image, there will be a camera that is digital, that is quantizing your ideal image, and then also this camera is sampling the image. So it is not well, it is sampling, and there is also quantization in the real values. So at the end, your imaging device is, or your final image is determined by two things. One is the imaging device. So the imaging device is doing some operations on the ideal image. The other one is the recording device. So the recording device also introduces artifacts in the recorded image. So at the end, what you have is something that we will call the discrete real valued image. So discrete because it is discrete in two aspects. One is space, and here it is represented with these squares. The other one is values. So not all values in the not all possible intensity values in the real world can be represented in the computer. And this is what it is meant here. So you have the image at discrete locations, and for the moment we have not introduced in this slide the quantization of colors. So far those colors are continuous, but we will quantize those colors into discrete values. So here is all possible values between yellow and red, for instance. But then in the computer, you cannot have all possible values, but you have a quantized version of that gray or that color scale. and here it is exaggerated just to 8 values. But the idea is that all these colors, that there is a whole continuum of intensities from this point to this point, they have to be mapped onto a single value that is represented at the computer. So this is if we quantize with just 8 values. In computers, normally we quantize with 16 million colors, so you don't see this effect so obvious as in this slide, but the effect is there. So you cannot represent it in a digital image all the possible intensities that are present at the sensor. So you would have an ideal image that is the one that the lens is projecting, but then the recording device, the camera, is sampling it. So it is discretization in space, and it is also quantizing it. So if we forget for the sampling and we get just the ideal image and we quantize it, then we are having this loss of information. So this loss of information applied at all possible points would give you, instead of a gradient, a very smooth gradient going from yellow to red, you would have a gradient that goes in steps. Okay, and these steps can be very small. This is what happens with the 16 million colors, but those steps are there. And the real image that you have in the computer is the composition of the two effects. So there is a stirring due to the colors, and there is also some quantization in space. So what you have is both effects combined. So this is the image that you have at the computer with very small steps. So the steps in space and in colors, they are very small, so you normally don't realize, but those are quantized versions of the ideal image that we would have recorded in an analog world. So I'm sure, so can you give me an example of digital acquisition and analog acquisition? So an example of digital acquisition. Your cameras in the phone, right? And so your cameras in the phone have this kind of images. An example of analog acquisition.
Voice recording.
Not voice recording, but regarding images, using images.
The old cameras that created the picture
on film. So when you do film recording on film, that is an analog acquisition, more biomedical oriented.
X-rays or
X-ray radiographs. So the radiograph is a continuous acquisition. Okay, good. So we will also see along the course that when you have an image like this one, if you zoom and zoom and zoom, at the end you see these small steps in space. And for each one of these small steps that they are called pixels, pixels comes from picture elements, this thing here. So the contraction of picture element is pixel. So for each one of these pixels, what you have is you have to encode the color. And a very common encoding is this RGB. So it is how much red intensity you need, how much green intensity you need, and blue. And so you keep 3 numbers for each one of the channels. So you would have, for instance, for this particular pixel, if I want to reproduce that kind of brown there, what I need is an intensity in the red channel of 206, an intensity in the green channel of 128, and in the blue channel of 9, and the same for the rest of the colors. And these numbers, they typically are they go from 0 to 255, and that is why we have the 16 million colors, because let me try this thing. So let's say that we have 3 channels, and we have 8 bits for each one of the channels. I don't know where it is. So we have the 3 channels, and then I have 8 bits for each one, 8 bits, 8 and 8. So we have 2 to the 8 possible values in each one of the numbers. And these 2 to the 8, they go from 0, 1, and then all the way, which is the last number, it is 255. But if you want to put it as a function of 2 to the 8, which one is it? 2 to the 8 minus 1, right? I'm going to 2 to the 8. 2 to the 8 minus 1. Okay, so how many different numbers, how many different tuples of 3 can I have with those? Two to the 3. 2 to the 3.
255 to the
156 to the 3. Okay, so the possible number of combinations is 2 to the 8, 2 to the 8, 2 to the 8, that is 2 to the 24, and this is 2 to the 4 times 2 to the 20. This is approximately 1 million, approximately, and this is 16, so that is why you have 16 million colors. So, but this is only if you quantize with 8 bits each one of the channels. Okay, so we come back to our image, and gray images, they have a property. If you put the same number in the 3 channels, what you have is a gray value. It's a gray color. So this gray color, it goes from completely black to completely white. So completely black is 0, 0, 0. Completely white is 255, 255, 255. And if I put a number in between, so for instance 107, 107, 107, I get this gray. If I put 75, 75, 75, I get this gray. And then, since the 3 numbers are the same, I don't need to pick the 3. I just pick 1, and I know that I have to repeat it 3 times. So gray images are made of a single number, not 3 numbers as color images. Okay, and then we will have some lectures related to color and how colors are constructed. And this is a concept that probably you already know, that if you combine light of 3 different colors, red, green, and blue, in different intensities, you can have any possible value, any possible color. But this is if you add light. We will see many other color schemes in which instead of adding light, you are subtracting light, but it will come with time. So, for instance, if you combine red and green, you get yellow. But for this yellow to happen, you need the same intensity in red and green. Okay, so if you have the same number of photons in green, same number of photons in red, then what you get is yellow. Otherwise, what you get is a different color. And the same happens for all the other combinations. And if you want to have a full color image like this one, then at every point, what we are having are these combinations of different intensities at the different of the different channels. And then we will see a bit about the technology of how color images are produced. So, for instance, this is this CRT technology. Do you know which one is that? CRT? Cathode ray tube. Does it make any meaning to you? The old televisions. The old televisions, they use this trick. So they had different phosphor layers, and then in each one of the layers, they had a number of points. And so it was discrete in space, and they were controlling how much intensity each one of these pixels were getting. And actually, the current technology is not exactly this one, but still it has a resemblance to this one. So the same ideas apply now. So you have 3 different channels, and the 3 different channels are displayed by 3 different devices. They are very much close to each other. They're actually, for instance, they can be on top of each other, but you have 3 layers. One of them is emitting in red, the other one is emitting in green, and the other one in blue. And each one is discretized, and each one of those points is emitting a different number of photons. So what you get at the end is something that is a mixture of the 3, because the 3 are on top of each other, each one is emitting at the same time. So what you get is a combination of the 3, and if you get pretty close to it, you would see the points, but if you look from the distance, you don't notice the separation of those points anymore. Actually, we will see it later, not later today, but later in the course. But our eye is doing a low-pass filter. So a low-pass filter means you cannot detect the high-frequency details of the image. So you don't see the points, isolated points anymore. But what you get is something more like a blurred version of the true image underneath. So that is why you don't see these individual pixels, and what you get is the impression that you have a continuous color image. But the same happens in all devices that you have on computers. So all this effect is happening all the time in all devices. Then we will see some operations that are called point processing. So point processing takes every one of those pixels and applies a point-wise operation. So it takes that point, applies an operation, transforms the point into another point, and we are representing this new point. So let's say that we have this original image, and we will see how to increase brightness, or how to decrease it, or how to increase the contrast, how to decrease it. And we will see more operations that may not be already familiar to you. So for instance, we can increase something that is called a gamma, or we can decrease gamma, or we can do operation on the histogram of the values there. So we can do histogram equalization, histogram modification. We can do many operations, but all these operations operate at the level of pixel. So we take every point and we transform it into something else. And then we will see a bit of how the eye is processing light and how we perceive colors. And here are some videos on how the retina is working and how images are formed. And we will see later a bit of the anatomy of the eye and why we are more sensitive to some colors than others, and how that affects the quality of the images, or how can we can exploit actually our eye sensitivities, if you want, to reduce the size of the images, for instance. And these are the typical responses of different kind of sensors we have. So here what is represented is our fovea. So the different colors are different kinds of cells. So So these green cells are more sensitive to the green light. These are more sensitive to the red light, blue light. These are the rods and cones you may have heard. So those are the spatial distribution of the rods and cones. And this is the frequency response of those cells to light. So for instance, cones are more sensitive to blue light. So when you excite those cells with light in this wavelength, that is blue, basically blue, you get a high response. But otherwise, if you excite the same kind of cell with different kind of light, they don't respond at all. Okay, and then we will exploit this cell response to organize the colors in some sensible way, and we will see different ways of encoding colors. So we have been talking about the red, green, and blue channels, but those are not the only way. There are many other ways, like we will see the details later in the course, but we will have something called luminance, that is more or less number of photons. It doesn't matter the color of those photons. And then we have two other variables that we will call hue and saturation, that somehow encode what is the color. So this one is encoding number of photons, while this one is encoding the nature of those photons, what are the wavelengths of those photons. And actually our eyes sees in RGB, but the brain sees in something more like intensity and color separated. So it separates intensity and color. And we will see all that. And here are some examples that we will explore to see how sensible we are to different reductions of information in each one of the channels. So, for instance, we have reduced the amount of information by factor 16, and in the red and blue channels, we are barely sensible to that reduction, and there is 16 times less information in the red or blue channels here than in the original image. But we are very sensitive to the green one, and we will see all these. And we will also see operations that work over colors. So these are like the point-wise operations that we were talking before, increasing brightness or contrast or whatever, but now at the level of colors. We will see more color transformations, and yeah, so a bit of the mathematics behind these color transformations. And one of the important operations that we will see will be the 2D Fourier transform. So the 2D Fourier transform looks like, the formula looks very much like the 1D Fourier transform, but now instead of having one spatial or one time variable, we will have two spatial variables, and instead of having just one frequency, we will have two frequency variables. And the same concept applies to 3D, 4D, whatever. So you can do the Fourier transform in any dimension, just extending a bit the formulation of the Fourier transform that you already know. And you know that the Fourier transform is based on the decomposition of a signal into sinusoids. So we will explore a bit what is a 2D sinusoid. And I already advance you that that a 2D sinusoid is something like this. It is a function like this one. So it is a repetitive wave, and it has some period that's like the 1D waves, or so the inverse of the period is the frequency. They have phase, so they have the same concepts as in one dimension, only that now they have a propagation direction, and that is what is giving it this to the two frequencies. That we will see all these details later along the course. So we will have also this concept of phase. So the phase in one-dimensional sinusoids is where the sinusoid starts. We will have the same. So for instance, here you have the 2D sinusoid whose maximum is at the origin of the space, but now the maximum is a little bit shifted, and that is the phase shift actually. We will see what is interpretation of the Fourier coefficient, that you know it is a complex value function. So what is interpretation in the frequency space? We will relate all those complex frequency components to properties of the 2D waves that make up the original input image. And we will see how to apply that Fourier transform to real world images. So you have an image like this one, and then you can decompose it in magnitude and phase, as you can do the same for the 1D signal. Then we will make some distinctions, as you have already done, between the continuous Fourier transform, the discrete Fourier transform, and all these families of Fourier transforms. And so we will have the continuous, the discrete, and we will see the convolution. The convolution that we have seen in one dimension can also be extended to several dimensions. We will see the connection of the convolution with the Fourier transform, that you already know the relationship. So you know that the Fourier transform of a convolution is the multiplication of the two Fourier transforms. So we will see those kind of properties. Then, in the same way as you can have aliasing when you sample a one-dimensional signal, you can also have aliasing when you sample images. So this sampling that the device is doing, that the digital camera is doing when acquiring the image, may induce some artifactual frequencies. So an excess of energy at some frequencies that are caused by the distance of the sampling. So we will see all these details too, and we will see also with some examples like this one. Here you can see, for instance, this is a grid that this train is having at the front. So you can see this grid. Here there is no aliasing, here there is aliasing. So you see that the grid cannot be like this in reality, and this is just an effect of the sampling. And we will see how to resample. So when you do upsampling or downsampling operations in 1D signals, we will learn how to do that in 2D images too, and we will see that we are much more, not much more free, but probably we will see different techniques to the ones that we have already explored for 1D signals. And then we will use these operations to resample. So this resampling, we will use some operation that is called interpolation. Interpolation is already named that you are familiar with. No? You know what interpolation is? Okay, so that's, well, we will see it in more details later. So we will use this interpolation to apply geometrical transformations to images, like a rotation. These are more fancy geometrical transformations, like image warping. So for instance, here you may see that the lines of this wall, or the borders of the wall, kind of converge to a point very far in the sky. But now we have made it more parallel. So you can do these nonlinear distortions to an image. And in general, this operation is called a warping. And for instance, we can merge images. So let's say that you have a couple of pictures of the same object and you want to combine them, but because of this perspective difference between this picture and this picture, you cannot perfectly overlap it. And then you need some image warping to make them fit. So we will do all that. Then we will also do filtering in the frequency domain. So those are the low pass filters, high pass filters, band pass filters that you already know for 1D signals, but now we will design them for 2D signals. Here you have, for instance, an example of how an original image, if you low pass filter it, how that thing looks like. And this is a high pass filter. We can do many other kinds of filters. So for instance, we can boost the high frequency. So this is not only a high frequency, so a high pass filter blocks the high pass filter blocks. So a high pass filter, the frequency response is something like this. So if this is the module filter and this is frequency, it is something like that. This is the ideal high pass filter. So the low frequency components cannot pass the filter. But instead of doing that, what you can do is start at 1 and start growing. So the high frequency components, they are boosted with respect to the low frequency components, but the low frequency components are not removed. So this is a kind of image enhancement that these that we have used to do this sharpened images. Then what else do we have? Then we can do band pass filters and sharp masking that we will see what it is. It is kind of having this filter in Fourier space designed in a particular way. And we can use these filters to estimate and to correct for motion blur, for instance. So if something is vertically blurred, or some part of the image has been blurred, but the other part of the image has not, or there is kind of zooming blurring. So you acquire the picture at the same time as the lens is zooming, or the camera is rotating while you are taking the picture. Then all these are different kinds of blur. They translate into different transfer functions in the Fourier space, and we can correct for those. We can reduce noise. So for instance, let's say that we have an input image with noise, and this noise is in the 3 channels, so we have color noise. So we can apply different operations to remove that noise. And you can see that some of them are more appropriate for particular kinds of noise. And we can have periodic noise, for instance. We can have an interference of some other device during the acquisition, and we can remove that periodic noise. And we can have, this is a very typical noise in images. This is called salt and pepper noise. So some of the pixels are dead. So dead means either they, so you may remember in the display, this is not full size. So you may remember in the display of the 3 channels R, G, and B that we had pixels that were emitting different amounts of photons. What happens if one of those pixels dies? So it can die in 2 ways. One is that it doesn't emit at all, The other one is that it doesn't accept your modulation. So if you want to emit more photons, what you have to do is to modulate the current there so that it emits more or less photons. But if it doesn't pay attention to your modulation, it is emitting the maximum amount of photons, and then it is emitting a white pixel. So it can die in two ways. One is going to 0, the other one is going to 255. And if you think of, for instance, so let's say what is the probability that a pixel dies because of some mismanufacturing process. So there is a problem, a failure during the manufacturing of that pixel, or it dies for any other reason. So let's say that you have a relatively low probability. So let's say it is 10 to the minus 6. If you have how many pixels you have in your camera? Typical size is 32 millions, let's say. 32 million. So 32 million and 1 pixel every million has a failure, has a probability of failure. So on average, you have 32 pixels in your camera that are there, and you don't realize because there are some image processing operations that remove somehow those pixels, the effect of those pixels. Okay, so here you have, for instance, this is what your camera collects, and this is what you see. So there are some ways of identifying those pixels and interpolating what the value in the middle is. Okay, so we will see many other different kind of filters. And to the end of the course, we will see different kind of operations that are those that I told you that are more specialized for images. So those are the ones that in one signals you can do them too, but they are not so common to do. But for images, they are very common. And they're called, in general, binary morphology. Binary morphology, for instance, what we can do, let's look at this object here. So we can dilate it. So we can take this object and make it larger. And we can erode it. Erode it means take this object and make it smaller, for instance. And then we can combine these two operations in many different ways. And we have other operations like opening, closing, dilation with the complementary of your kernel. And we can extend this binary morphology to gray morphology. We will do it in the next slide. So here is some application of this binary morphology. So using these operations, we can do things like this, for instance. So let's say that we have an original image that has some isolated pixels. We can identify those isolated pixels and get rid of them. We will do that with these binary operators. And we can extend the concepts of morphology to non-binary sets. So the sets that are defined on the grayscale. So here you have an example of how it would look like. And then the last lecture will be on image compression. So image compression, for instance, if you acquire an image that has this number of pixels in width, this number of pixels in height, and then the raw data would occupy something like 120 megabytes, but we can make it much smaller. So for instance, this is a zoom of that image, and we can do it as small as 12 kilobytes. So this is 4 orders of magnitude smaller. So this is 100 mega, this is 12 kilo. So from mega to kilo we have 10 to the 3, from 120 to 12 we have 10. So we have 4 orders of magnitude less space, and still the quality of the image is quite good. So we will see how to achieve this compression without compromising too much the quality of the image. And here you have an example. And yeah, so this will be it. Any question? No? Okay, so I think I have given to you all the material you need for the moment. So I think in this group of teams you have the introduction to the course. This is all the rules that I was showing before of what are the evaluation and what are the yeah, mainly the evaluation is the important part there. And I have given you also the, how is it called? Yeah, there are similar, but okay. So, well, what is the official contract for the course? And that is the diagram. And the slides. So the slides are also there. And then for the practice, we will do it in MATLAB. I understand you have a MATLAB license, right, at the university. And then do you have any specific version of the license, or you have the updated 2021? No?
Creo que es 2020, porque nos las dieron el año pasado, pero no sé.
But do you have a license that you can renew somehow? So you can renew the installation? Probably, yeah, I think they release in, I don't know, if it is February or March or something like that, and then 6 months later. So probably the latest version is 2020, but at some point they will release 2021. But my question is, you have last year, for instance, license, okay, good. And then I will show you, are you familiar with Git? Do you know Git? GitHub? Yeah? Have you used GitHub before? All of you? Okay, so I don't have to explain how a repository works. Okay, so I will show you how to work with the repository within MATLAB. And then we will create all together for the practical, we will create a tool that allows illustrating all these ideas of image processing so that I can make it live. Okay, so that will be the practical this year.